All right, guys, let's go ahead and go over today's warm-up question, which you can see on my screen right here. It says, a baseball player bunts. The forces acting on the ball during the time it contacts the bat are shown. And we see an applied force there of 25 newtons to the right. It's in green. And we see Fg, the weight of the baseball, in red as 3 newtons. And the question says, what is the net force acting on the ball? When we took notes 2 days ago over this same unit, I told you that there would sometimes, or whenever we calculate net force, you have to calculate it separately for the horizontal and vertical direction. So if you have a horizontal forces, more than one, you get your net force in the x direction, the horizontal, and you do the same thing vertically. But if you have both a horizontal and vertical net force like this, then you're going to have to solve for the resultant by using vector addition. It's going to make a right triangle, and you're going to draw in the hypotenuse. Okay, and that will be your net force, that resultant vector. That means you're going to have to use a squared plus b squared equals c squared. And then you're also, because force is a vector and vectors have direction, you're also going to need to calculate what the angle is of the vector, meaning we're going to have to use some trigonometry. We're going to use SOHCAHTOA today, which is why I'm telling you to have paper out so you can take notes. Okay, because we're going to be bringing in some of the math that may not be your favorite. I don't know. But let's go ahead and go over this warm-up, and then once we get to the end of the period, there is an assignment, 301.2, but it's not due until Monday. So we're doing notes today and some more practice on Monday that's similar, but you'll be able to start the assignment over the weekend. Okay, so back to the warm-up. If you are trying to solve for the net force here, I already mentioned that we're going to have to use some vector addition. You can't add these as they are. Okay, if you're doing vector addition, you have to draw the vectors head to tail. That means that I have to place my red vector needs to start where the blue one ends, or vice versa. The blue one needs to start where the red one ends. I can't have them both originating at the center of my free body diagram. Okay, so I can't leave them like this. Instead, I'm going to redraw them like that. And you could have redrawn the blue one instead. It doesn't matter, but as long as you add them head to tail. Okay, if you had done it the other way, you would have your red vector pointing down here still, and then the blue one would be going over here. Notice it would just be the other half of this rectangle. Okay, by the way, these are not drawn to scale, so if you want to draw them more to scale than I did, that is fine. But 25 and 3, that red one should be a lot shorter than that blue one. Not just a little bit, but that's okay. So again, to find the net force, we're looking for this green resultant vector that we get when we add the other two vectors together. And we can solve for that using Pythagorean theorem. Anytime you have a net force in both the x and y directions, like I do here, I have a horizontal force and a vertical one. Anytime that happens, you're going to have to use Pythagorean theorem in order to solve for the magnitude of the resultant net force. As a reminder, that's a squared plus b squared equals c squared. We're solving here for c, which is the hypotenuse of this triangle. And so I have 25 squared plus 3 squared equals c squared. 25 squared is 625. 3 squared is 9. I add those two things together, I get 634, but again, that is c squared. So if I want just c, I need to take the square root of both sides, and this gives me 25.18 newtons as the magnitude of this resultant net force. So when I add these two forces together, these two vectors together, I get a total net force of 25.18 newtons. But as I mentioned a moment ago, vectors have direction, okay? And so does this net force. It's a vector, it needs a direction. And yes, it is to the right and down, but that is not specific enough. How much to the right? How much down? Yes, I know I have those numbers, but we're going to define our resultant, 25.18 newtons. We're going to add an angle to that so that we have the exact picture of where this vector is pointing. Okay, so again, forces are vectors. They need a direction, so we need to solve for an angle. You can add in an x and a y-axis. That's going to make it easier to label the angle. So you'll notice I added in some dashed lines, and I'm just using directions here of up, down, left, right. I'll do another example in a moment that uses north, south, east, west, but the process is the same. You can label your directions based on the question that you're answering. So if the question is using words like left and right, you can label it like that. If the question is using words like north and west, then you can label it with cardinal directions instead. But we need to solve for an angle. So we're going to find the angle from the nearest axis. That's going to be right here, this angle where my red cursor is. So we're going to solve for theta. So now we have an unknown angle that we need to solve for, but we do know the sides and hypotenuse of this right triangle. So we can use SOHCAHTOA. Again, if this is something that is a little rusty for you, then I would encourage you to copy down this example so that you have it. Okay, if it's something you have never seen before, then you're going to be trying to learn this on your own, because I am not going to spend the whole period talking about SOHCAHTOA. Okay, you come in here hopefully already having learned this in your geometry class and then again in pre-cal. But that's the mnemonic device that you use to remember the equations. So if you don't remember, here they are. You're welcome to write them down if it's something that's a little rusty. Again, the SO in SOHCAHTOA stands for sine of the angle theta equals opposite over hypotenuse. So that is the SO, S-O-H, sine opposite over hypotenuse. The CA in SOHCAHTOA is cosine of the angle theta equals adjacent over hypotenuse. So it's your adjacent side divided by your hypotenuse. The TOA is tangent of your angle theta equals opposite over adjacent. So that's the equations. If you can remember SOHCAHTOA, it is, again, a way to remember those equations. Because I know all three sides of my triangle, I know the opposite side, the adjacent side, and the hypotenuse, I can actually use sine, cosine, or tangent, because I know everything that I need for each of them in order to solve for my angle. However, my hypotenuse, 25.18, is a value I calculated and that I rounded, and so I would prefer not to use that one, because if you do, don't use the rounded one. You guys already know that my open math penalizes you if you're off by a couple decimal places. So if this was a problem for my open math and you rounded that 25.18, you would want to use the whole value from the calculator for your calculation. You'd be good then, or just use the other two values that aren't rounded, which is what I'm going to do. Okay, so I am going to use tangent, but again, you could use sine or cosine as well. When you're doing these calculations, you do need to make sure that you are in degree mode on the calculator. And guys, I know that y'all like to use Desmos for your calculator. However, please keep in mind that you cannot use Desmos on your quiz or on your test. So I would strongly encourage you to use the same calculator that you plan to use on the quiz or test. If that is your own calculator that you brought from home, cool. If it is one of mine, I would encourage you today when we get to the practice to actually get one of those, or you can even go grab one right now so that you know how to do this on an Inspire. Okay, because if all you know is Desmos, you're going to be in trouble when it comes time to take your test. All right, so by the way, if you are using a TI Inspire, there is a button on that calculator that says trig. That's what you will push. You will see sine, cosine, tangent, and inverse sine, inverse cosine, inverse tangent. Yes, sir.
Can I go to the restroom? I can see on the line and see how I can do it.
Yeah. All right. So, again, for this particular calculation, we're doing tangent of our unknown angle theta, and tangent is opposite over adjacent. It's the TOA in SOHCAHTOA, so that's 3 over 25. So I'm trying to solve for theta here. If you're trying to solve for an unknown angle, you're not going to type tangent in the calculator. You're going to type inverse tangent of that, 3 over 25. That's how it goes into the calculator when you're solving for theta, okay? Because you have to get theta by itself. You have to do the inverse tangent of that. Okay, so you have theta equals inverse tangent 3 over 25, and if you're in degree mode and you put that in the calculator, it should give you 6.84 degrees. Again, I've rounded that value, but that is the angle, and that makes sense. Look at the dimensions of your triangle. 25 by 3 is going to be a long, skinny triangle with a small angle. So you can make sure that it makes sense. I know mine's not drawn to scale, but it does make sense that it would be a small angle like that. All right. So again, now we have an angle and we have a magnitude, 25.18. We have to put them together in order to give our final answer for net force. I need them both in the same answer. I need magnitude and direction. But I also need to better define this direction. 6.84 degrees from what? Okay, you have to describe it from some sort of reference. And because it is measured in my diagram right here from this horizontal axis, you can say below the horizontal. Now, if I had drawn the triangle above the axis, if that red vector was pointing up, you would be up above it. You would say above the horizontal. But here I'm below the horizontal. So if I want to give my final answer, it looks like that. Bottom left of my screen. The net force is 25.18 newtons to the right at 6.84 degrees below the horizontal. That is a very precise description of that vector. I know now exactly how much force there is and exactly where it's pointed. Okay, to the right, 6.84 degrees below the horizontal. All right, so again, that is how you solve for net force. Now, obviously, this question is pretty much separated from the rest of the physics content. We're just practicing the trig right now. So usually this will be part of a larger calculation. Okay, but I want to practice the trig a little bit more with one more example that looks like this, and then we'll look at those larger calculations that also involve angles. But does anybody have a question before I move on? Yes?
How do you get it into degree mode?
On the Inspire, there next to the battery indicator, it'll say DEG or RAD. You can use the touchpad to bring the mouse up there and click on it and change it that way. You can also go to this menu, Doc 7.2, and it's in there as well, in document settings. All right, let's try this one. Okay, similar to the last problem. We have two vectors here, a 6 Newton vector pointing up and a 9 Newton vector pointing to the right. I'm going to draw them again head to tail, so before you do the vector addition, please redraw them so that your hypotenuse is drawn correctly and you can get the direction correct. Okay, so now I have this. I always move the shorter vector to the end of the longer one. That's what I do. You don't have to do it that way. Again, if I did it the other way, I'd have 6 up and 9 over. It would still be in the same spot. The magnitude would be the same, but I would be defining a different angle. It would still be right. They're going to be complementary to each other. All right, so again, I'm looking for this blue vector. That blue vector is my net force. It has both magnitude and it has direction. I need to find both, but let's go ahead and find the magnitude first using Pythagorean theorem. A squared plus b squared equals c squared for this problem is 9 squared plus 6 squared equals c squared. That is 81 plus 36, which is 117. So c squared is 117. Again, I want c, so I'm going to take the square root of both sides, and that gives me 10.82 newtons. So that is the magnitude of the net force for these two vectors, 10.82 newtons. Again, force is a vector, it needs a direction as well. So we've got the magnitude, but now we have to figure out the angle. Okay, so we're going to do cardinal directions this time. You'll notice, by the way, I labeled my 10.82 on my diagram. But instead of using up, down, left, right, you'll notice I have north, south, east, west, because sometimes the questions you're solving will use these directions instead. Okay, so I have my directions labeled. Let's go ahead and see if we can calculate the angle this angle right here, nearest to this east vector. So we're solving for theta again. All right, again, SOHCAHTOA. I can find theta using sine, cosine, or tangent because I know all three sides of this triangle. But once again, the hypotenuse has been rounded. I would prefer not to mess with those decimals, so I'm going to use tangent again. But there is nothing wrong if you want to use one of the other ones. Just use the unrounded value from the calculator instead of 10.82, 10.819, whatever. Okay. All right, when I solve for this, it looks like this. Tangent of theta equals opposite over adjacent. That is 6 divided by 9. But again, I'm solving for theta. So in my calculator, it ends up going in like this. Inverse tangent of 6 over 9 And if you're in degree mode, that is 33.69 degrees. You're welcome to try it on the calculator that you have at your desk. But that is your angle. Okay, again, angles need to be described with a direction, 33.69 degrees from what? Okay, because that by itself is not very much information. So to specify direction, again, do it with respect to some reference. I'm going to use the axes I drew in, just like last time. Okay, but this time, instead of calling it the horizontal, I'm going to call it east because it's the east line. Okay, and we're going to say that it is, because it's above the east line, we're going to call it north of east because that's the directions I have on my screen. It is on the north side of east. If it was below it, it would be on the south side of east. So I'm going to call this angle 33.69 degrees north of east. And now we can put it all together to get our final answer. The net force is 10.82 newtons at 33.69 degrees north of east. Questions about that? Yes?
Will the opposite always be like the one
No, I mean, typically you're going to have the two components, but if you're solving for net force, but sometimes you have the hypotenuse and the angle, and you might have to find the two legs, which is what we're going to do in the example in a moment. So you'll see it there. Yeah.
This also might be a dumb question, but how are you always going to be able to tell, like, what is, like, the north and, like, the south of, like, a direction?
Sorry?
How are you always going to be able to tell, like, the north or south of a direction?
It'll be defined in the question. So the question might say a car is driving 9 meters, if it was direction, it might say 9 meters east and then turns and goes 6 meters north, and then it might ask for what its displacement is, and you could do it the same way.
Like,
So,
how in this case do we know, like, north?
sorry?
Like, I can tell, like, how it's east, but how do we tell that it's, like, oh, wait, never mind.
Because it's above it.
Yeah.
Yeah. All right. So let's try a calculation without an angle first to kind of ease our way into it. We haven't done much math with this yet. We're going to bring friction into this calculation because we only did one example with that a couple days ago. So if you want to copy this down, it'd be a good one to have with friction. Then we're going to look at a similar problem where the ice is being dragged at an angle. So we're going to add an angle in. This one says a large block of ice is being pulled to the right across a frozen lake. The block of ice has a mass of 250 kilograms. The coefficient of friction between the two ice surfaces is small. The coefficient of friction mu is only 0.05. What is the force of friction that is acting on the block of ice? Anytime you are reading a question like this one, I'm going to strongly encourage you to start with a free body diagram. You can label stuff first and then do the free body diagram. I don't care. But before you do any math, you're going to label things like normal. You're going to draw a diagram. Okay, that's an additional thing that we hadn't had to do in our previous unit, but you do need to do it now. Okay, so I know my mass. I know mu. Those are the only things given to me in the question. I also happen to know an equation for force of friction, which the question is asking me for. Force of friction is mu times normal force. But the problem is I don't have the normal force. And that's where the free body diagram comes into play, because if we draw it, we might see a way to figure out what our normal force is. And so that's what you're going to do next, is draw that free body diagram. And it should look something like this. Okay, I have my ice block. I have force of gravity down. That's the weight of the ice block. I have the tension that is described because he's pulling it to the right with a rope. I have friction that's described. It gives me a coefficient. I know there's friction. It will be opposite the motion. And I have to include normal force. Just like in your lab yesterday, whenever you were dealing with the shoe, you were pulling the shoe, same type of thing. Okay, your diagram actually yesterday for pulling the shoe probably looks pretty similar to this, by the way. Okay, if you were accelerating the shoe. But whenever you draw those diagrams, is this ice block accelerating vertically? Up or down? No. Was your shoe in your lab accelerating vertically? No, same scenario. If you don't have vertical acceleration, when you draw this diagram, you need to draw it so that your vertical forces are balanced. I'm helping you out right now with your RA if you got stuck. Okay, so Fn will be equal and opposite to Fg because those are the only vertical forces that we have. Okay, so when you draw it, you can add a little equivalency mark to show that they're the same, or you can label them with the same number if we're doing a calculation, which we are. All right, So because I know Fn is the same thing as Fg, they have the same magnitude, I can actually calculate Fn because I can calculate Fg. Fg is mass times gravity. It's the same way you calculated Fg in your lab yesterday for your shoe. Mass of your shoe times 9.8. Same thing here. And yes, it is negative 9.8. Okay, but whenever we're labeling our diagrams, you're going to probably have to pay attention to the sign after the fact, because I'm telling you this is the same value for Fn and Fg, but they're both not negative. They're not both negative. Okay, so I didn't bother writing the negative here. I'm just multiplying them out, and I'm getting 2,450 newtons. For Fn, that's up, so it's positive. For Fg, that's down, so it's negative. Okay, so again, if you were labeling it for one of those, you could base the direction on your diagram. So draw the diagram so that you can see which ones are negative and which ones are positive. All right, so now that we have Fn, we can find force of friction. It's mu times Fn. Mu is in the question, 0.05. Fn, we just found it to be equal to Fg, so we use the Fg equation, and we got 2450. So if I want to solve for friction, I'm going to multiply these two things in my calculator. 0.05 times 2,450 is 122.5, but you'll notice I wrote a negative sign in front of mine. Your calculator is not going to tell you this is negative. That's why the picture is so important. When you are giving answers for forces, look at the diagram to figure out if it's negative or positive. My friction is pointing to the left. So even though my calculator is not going to tell me it's negative because mu and normal force are both positive, okay, I need to check the sign after the fact, and you do too. So that's why I have a negative in front of it. Negative 122.5 newtons because it is to the left. And again, friction's always opposite the direction of motion. Since it's being pulled to the right, friction will be to the left. The left is the negative direction. Questions about that? Okay. All right, so let's do some follow-up questions. What is the net force on the ice block, and what is the tension force pulling the ice block? And I added one more piece of information to the question. If the acceleration of the ice block is positive 2.5 meters per second squared, we need that because there are two ways we can find net force. We can find net force if we have all of the vectors in our free body diagram labeled, because then we can just add them together, horizontally and vertically separately. But I don't have tension, so I can't do that. The other way to find net force is F net equals ma, which is why I gave you an acceleration. You already had a mass, so we're going to use F net equals ma to find net force with the mass and the acceleration in the question. And then we can find tension, because guess what, guys? There's not an equation for tension. There's only equations for friction, force of gravity, and spring force. So if I ever ask you for an applied force or a tension force or anything else that's not those three, you're going to have to do it from the diagram based on the net force and then say, okay, the net force is these two added together, let's subtract that one out. Okay, so there's not an equation for tension. We have to get net force first. So let's get net force. F net equals ma. We know the mass, 250. We know the acceleration, 2.5. Check those units. They look good. Kilograms and meters per second squared. 250 times 2.5 is 625 newtons, and it will be to the right because the block is being accelerated to the right. It says so in the question. All right, so we have our net force, 625 or positive 625 newtons. That's the first question. The second question says, what is the tension force pulling the ice block? Again, there's not an equation for tension. Don't bother looking, it doesn't exist. Instead, we're going to use the net force we just found and the forces in our diagram. Now, that net force is horizontal because vertically, my net force is 0. So all I'm looking at here are these horizontal forces. If you're trying to solve for net force from your diagram, or if you're trying to find one of your forces from the diagram when you know the net force, this is your basic equation for net force horizontally. Your net force in the x direction, the horizontal direction, is simply all of the forces that you have that are going to the right plus all of the forces that you have that are going to the left. You're just adding together. It's the sum of the forces. Keep in mind, forces to the left are negative. So when you're adding it, you're really subtracting. All right, with that, this is what that looks like. My net force is 625. I found it just a second ago. It's equal to Ft plus my force to the left, which is negative 122.5. Okay, so when I go to solve for this is actually Ft minus 122.5. I'm going to add 122.5 to both sides, and that will give me force of tension of 747.5 newtons to the right. So my tension is 747.5. My friction's canceling out 122.5 of that, and that's how I get my net force of 625. Double check it afterward, make sure it makes sense. Okay, you know the net force, and then you can just go backward and add them together again. Make sure you still get 625. All right, so again, that's how we find tension here. Questions about this one? Let's add an angle. Okay, now we have an ice block being pulled at an angle. It says a block of ice is being pulled to the right across a frictionless surface. So that was nice of me. I took friction out. Because the hardest this could be is if we also included friction. So I didn't bother doing that. Okay, we took part of it out. But pulled at an angle across a frictionless surface with a force of 183 newtons at an angle of 25 degrees above the ground. So that's going to be above the horizontal line. If the block has a mass of 40 kilograms, find its acceleration along the surface. You'll notice I've already labeled the information I was given in the question. I know the mass is 40 kilograms, and I know the force of tension is 183 newtons at 25 degrees. And I can see it in the picture too. They drew it for us there. So if I want to start analyzing this, I'm going to start with a free body diagram. Ice. Okay, and I'm going to draw the forces acting on that ice. And I always start with the same force because every single free body diagram I draw is going to have Fg on it unless I'm in space. Okay, so I'm going to have Fg down. Okay, I'm also going to draw the force that's described in the question. 183 newtons at an angle of 25 degrees. So I've drawn that one at an angle. Okay, so with that one you need to draw it at an angle. I also know that there should be some amount of support force from the surface of the ice. However, let me ask you a question again. Is this ice block accelerating vertically? Does it mention anything about vertical motion at all? No. It's just going along the surface. So I know that my vertical net force again has to be 0, but this time what that means is Fn is not equal to Fg. Because when I pull it at an angle, part of that force is also up. So that part that's up plus Fn are going to equal Fg. We're going to see that in a second. Okay, so just a heads up, Fn is not always equal to Fg. In fact, any time there is a push or pull at an angle, they are no longer going to be equal to each other. Okay, Fn will not equal Fg if there's an angle. So maybe make a note of that. All right, so what do we do here? Okay, if you have any forces at an angle, you must determine the horizontal and vertical components of that force. I need to know how much of that 183 newtons is sideways and how much of it is up. Because when we're looking at net force, we need it just X and Y, just vertical and horizontal. We don't want them at angles. So I'm going to redraw a triangle over here. There's my 183 newtons. There's my angle of 25 degrees, and there are the two components, the horizontal piece, which I called Ftx, and the vertical piece, which I called Fty. Okay, so we're going to have to solve for those two pieces. And again, this is where we come back to SOHCAHTOA. For the purple one, which is in the x direction, I'm going to use cosine because my purple vector is adjacent to my angle. And I know my angle this time. So I have cosine of 25 degrees equals adjacent over hypotenuse. It's the ka from SOHCAHTOA. My adjacent side is Ftx. That's what I'm trying to find. My hypotenuse is 183. If I want to solve for Ftx, I need to just multiply both sides by 183. So if you're following along with me, you would type 183 times cosine of 25 degrees in your calculator. And if you do that, and if you're in degree mode, you should get 165.85 newtons. Again, that's probably rounded, I don't remember. Okay, but I have 165.85 newtons. I added it to my diagram. We're going to do the same thing for my vertical vector, but the vertical one is opposite the angle. We have opposite and hypotenuse. That means we're going to be using sine. So the sine of 25 degrees equals FTY over 183. That's opposite over hypotenuse. This is the SO and SOHCAHTOA. If I want to solve for FTY, multiply both sides by 183. If you're practicing with me, that is 183 times sine 25. In the calculator, when you do that in degree mode, you get 77.34 newtons. So now I have the pieces. That 183 is at an angle. I can't use that, but I can use, and I have to use, the horizontal piece, 165.85, and the vertical piece, 77.34. I'm actually going to redraw my free body diagram with those on there, and without that diagonal one, so that it looks like this. Okay, so that diagonal one gave me those two pieces, FTY and FTX. Yes?
What do you type in the calculator for the purple and?
For the purple one, it would be 183 times cosine of 25. You're just isolating the variable, multiply both sides by 183. All right, so now that we have it redrawn, you can see how, what I said earlier, if my vertical net force is 0, you can see how to find Fn, because you know how to find Fg. We're not going to do that though, because we don't need it for this question. This question says find the acceleration along the surface. Acceleration along the surface is to the right. I don't even care about the vertical. It doesn't matter. Okay, for this question, all I care about is this 165.85 newtons because that is my net force to the right. And I have to use that along with the mass from the question to find acceleration. So that's what we're going to do. We're going to use F net equals ma, and we're going to use the net force in the x direction. Okay, so again, when you're solving a second law problem like this one, here's kind of this thought process for solving it. If you want to write this down, you can use this approach with all of these questions. Draw a free body diagram and break it into components if you need to. If you have anything at an angle, do what we just did and get the pieces. Okay, the x piece and the y piece. Those are the components. Only forces in x or y are allowed. Okay, then you're going to determine F net x and F net y. Again, F net x is 165.85 newtons. F net y here will be 0 because we already said there's no vertical acceleration. And then you can find acceleration in the x and y directions as well. All right, so again, focusing this part right here, 0. So we're going to focus just on Fx, and that's what it says here. F net y is 0 because forces must balance vertically. There's no mention of any vertical motion or acceleration. F net x is 165.85 because it's the only horizontal force. If there was friction, we would have to take it into account, but there's not. This question says frictionless ice. Okay, so that means our net force is that one force. All right, so here's my mass, here's my net force with all the decimals, okay, or at least more of the decimals, so we can solve for A. F net x equals m times ax. Plug in, that's 165.854 equals 40 times A. If I want to solve for A, I'm going to divide both sides by 40. 165.854325 divided by 40. Okay, gives me an acceleration, and it's up here, of 4.146 meters per second squared. Okay, so again, we had to get those components in order to solve this. That's usually what ends up happening is you have something at an angle, you have to get the components, and then you have to use that in order to solve for something, whatever it asks for. Questions about this one? Okay. All right, guys, that is it for today's notes then. This is slide 40 if you want to open it back up and look at that one again. Actually, I do have a follow-up question. What would the change in momentum be? First of all, would this ice block have a change in momentum? Let's start there. If it's accelerating at 4.164 meters per second squared. Yeah, because that means its velocity is changing. If your velocity changes, you have a change in momentum. Because it's changing positively, it's getting faster, it's being pulled to the right, we would say that it has a positive change in momentum. We could even calculate it. I'm not going to do that right now, but that is something we could add on to one of these problems. All right, as I said, that was it for the notes. So what you're going to do for the rest of the period today is get started on the MyOpen Math assignment 301.2, two-dimensional second law problem set. It's not due until Monday. Okay, the other thing you could continue working on is your 302 Forces Lab RA. That's due Tuesday, so you have the option to work on that right now if you prefer. And then just as a friendly reminder, you do have that optional bonus rocket project if you're choosing to do that. Your test grades are in the grade book. So if you didn't, they put them in yesterday. So if you haven't looked yet, take a look. If it wasn't so hot, this might be a good option for you. You can still retest. You can save the project for the third test. That's fine. It'll replace whichever one's lower between Unit 2 and Unit 3. But your retest only gets you a 70. The project will replace your grade up to a 100. So keep that in mind. All right, so if it wasn't as where you wanted it to be, please take advantage of this. I'm reminding you again now because you do have to purchase something for it. That's also why it's optional, but you have to get a stomp rocket. So you've got a couple weeks, but please don't wait until the last minute because you probably won't be able to do it. All right, so anyway, go ahead and get to work. If you have questions as you're working, please let me know.